In this video, we look at example 3.2.15. We want to solve the following linear system using Gauss-Jordan elimination. The first step is to write the augmented matrix of this system. So we have 2, 3, 1, minus 3, 4, 6, 1, and minus 2. Next, we want to reduce this augmented matrix to reduced row echelon form. Let's start by reducing it to row echelon form. We know that in order for this matrix to be in row echelon form, at least this entry in the bottom left must be a 0. And so which row operation will help us achieve that? Well, we can do row 2 minus 2 row 1. So we're going to get 2, 3, 1 minus 3. The first row is not changing. In the second row, we have 4 minus 2 times 2. That's 0. Then 6 minus 2 times 3. That is also 0. And then 1 minus 2 times 1. That is 1 minus 2, which is minus 1. And then finally, minus 2 times minus 3. So minus 2 plus 6. That is 4. And so this matrix is actually already in row echelon form. It is, however, not yet in reduced row echelon form. The leading entries are not leading ones. We have a leading 2 and a leading minus 1. And so let's take care of this leading minus 1. If we perform the elementary row operation minus row 2, that will become a leading 1. So we still have 2, 3, 1, minus 3 in the first row, and then 0, 0, 1, minus 4 in the second row. So now I have a leading 1 in the second row. Now that leading 1 is in the third column, and in that third column there is also this 1, which needs to be a 0 in order for this augmented matrix to be in reduced row echelon form. And so I'm going to use the elementary row operation row 1 minus row 2 to get a 0 in that position. So 2 minus 0, that's 2, 3 minus 0, that's 3, 1 minus 1, that is 0, the 0 I want, minus 3 minus 4, that is 1. So that's my new first row. The second row stays the same, 0, 0, 1, minus 4. Now this augmented matrix is not quite yet in reduced row echelon form. In the first row I have a leading 2, I do not have a leading 1, and so I'll use the elementary row operation 1/2 row 1 to get a leading 1 in that first row. So my new first row becomes 1, 3 over 2, 0, 1 over 2. The second row stays the same, 0, 0, 1, minus 4. This augmented matrix is in reduced row echelon form. And so next I will write the new system of linear equations. So I have x plus 3 over 2y plus 0z equals 1/2, and then z equals minus 4. That's my new system of linear equations. Now let's identify the leading variables and the free variables. I have 2 leading 1s. And so my leading variables are x and z, and my free variable is y. And so I will set y to be equal to t. And so now I will replace y by t. So I have x plus 3 over 2t equals 1/2, and z equals minus 4. This is my new system of linear equations, which I can now solve using back substitution. The second equation gives me that z is equal to minus 4. The first equation gives me that x is equal to 1/2 minus 3 over 2t. In this last back substitution step, I did not actually have to substitute equation 2 into equation 1. So reducing the augmented matrix all the way to reduced row echelon form simplified that last back substitution step. Now I can write the solution in parametric form. I have that x is equal to 1/2 minus 3 over 2t, y is equal to t, and z is equal to minus 4. And I can also write the solution in vector form. I have that x, y, z is equal to 1/2 0 minus 4 plus t times the vector minus 3 over 2, 1, 0. So in this example, we used Gauss-Jordan elimination to solve a system of linear equations with infinitely many solutions.